Now, if we have a carbon-carbon double bond in a structure, those compounds are called alkenes. And the way we're going to name them is we're going to look for the longest carbon chain, but that longest carbon chain must include both carbons of the carbon-carbon double bond. So now it's no longer just where's the longest carbon chain throughout the whole structure. Now that we have a functional group in the molecule, we need to incorporate that functional group into the parent. So the longest carbon chain must contain both carbons of the carbon-carbon double bond. And then we're going to number from the end that's closer to the carbon-carbon double bond so that the double bond will get the lowest number possible. Okay? After doing that, what we're going to do is we're going to take the A in the word alkane, methane, ethane, propane, butane, and we're going to change it to an E. And so we're going to call it an alkene instead. And we're going to put a number out front that tells the reader where the double bond starts. What's the first carbon of that carbon-carbon double bond? So we're going to call it a number alkene, or you can insert that number inside the name. This is actually kind of the preferred way for IUPAC, but I think it's a little more difficult for beginning students to look at that convention. So for example, our simplest alkene is a 2-carbon alkene. He has a common name. This is called ethylene. Ethylene is a gas that is generated by fruits in the ripening process. So ethylene is actually sprayed on fruit to help them ripen when they're picked earlier for packaging and for handling. So this is commonly known as ethylene gas, but the IUPAC name, it would be an ethane derivative because it's 2 carbons, and instead of calling it ethane, we call it ethene. So not a big difference between the common name and the IUPAC name, but the IUPAC name is ethene. So this tells the reader, that E tells the reader that there's a double bond in this molecule. In this case, I don't need to indicate where the double bond is because there's only one place for it to be, right, connecting those 2 carbons. This compound is commonly known as allyl chloride because you have a chlorine that's allylic next to a double bond. So it's known as allyl chloride, but let's do its IUPAC name. We have our 3-carbon chain is right here. That's our only possibility for our longest carbon chain. And when we go to number it, we're going to number it from the end closest to the double bond. So we'll start from this end, 1, 2, 3. And so 3 carbons means it's a propane derivative because of the double bond. We call it propene. So this is 1 propene. We're going to indicate the first carbon of the carbon-carbon double bond. So this implies that there's a double bond starting at 1 and going to 2. And what else do we have on here? We have a chloro group at carbon 3. So this is 3 chloro, 1 propene. Remember, there's dashes between numbers and letters. Sometimes we leave off the 1 in this case, and that might be implied, but it's a really good habit to leave that 1 in there. We don't want to make that assumption and make a mistake. So this would be the best name for that. Okay, how about this case? Where's our longest carbon chain that contains both carbons of the double bond? Looks like we'll come across here, but then we'll move down in this direction because that would be a longer chain than over here. And how are we going to number it? If we numbered it from here, our double bond would start at carbon 2. If we numbered it from here, 1, 2, 3, 4, it wouldn't start till carbon number 4. So we'd rather have it be at carbon 2, 1, 2, 3, 4, 5, 6. So a 6-carbon alkene is going to be called hexene. It's a 2-hexene. And by circling off and blocking off the parent, it's very easy for me to see what other groups are attached. We still have this 2-carbon group that's called an ethyl group. So at carbon 3, we have an ethyl. How about this next case? Our longest carbon chain would be this one, but the longest carbon chain containing the carbon-carbon double bond would be down here. So we have to make sure to include that. Okay, and how long is that? 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that's an octane derivative. We're going to call this 1-octene. And at carbon 2, we have a 1, 2, 3 carbon chain. That's a 3-propyl. 3-propyl 1-octene. Now, we can incorporate a double bond into a cyclic structure as well. Now, remember, with a ring, we have to decide where to start numbering our carbon chain. So one of the double bond carbons is going to be carbon number 1. and we're going to have to number through the carbon chain and then continue on to also give the substituent the lowest possible number. So if I numbered from here 1, 2, 3, 4, 5, 6, the substituent wouldn't be until position 6. If I numbered this way 1, 2, 3, I get the lowest number for the double bond. That has to be at carbon 1, and then I also get the substituent at the lowest number. So 4, 5, 6, this is a 6-membered ring. So we would call that cyclohexane because it's a ring. Because it has a double bond, we call it cyclohexene. Okay, and where is our group? What is this group called? The benzene ring is called a phenyl group. So we have a 3-phenyl cyclohexene. Now here's a case where we really don't need the number. The double bond has to be between carbons 1 and 2. That's how you define a ring. There's no other place to put the double bonds, and that's our highest priority. If you want to put that in there just to be safe, that probably won't hurt if you want. Okay, and what if we have 2 double bonds? If we have 2 double bonds, we're going to indicate both numbers of where the double bonds start, and we're going to call it a diene or a triene or a tetraene and so on. So we're going to include that. We're going to put that in there. And now again, we want to give our double bonds the lowest possible number. So and I need to give both double bonds the lowest possible number. So the only way to number this to give the double bonds the lowest possible number would be as so. 1, 2, 3, 4, 5. So what do we have on carbon 5? We have a bromo. We have another 5-bromo. We're going to call that a 5,5 dibromo. A 5,5 dibromo. And then at carbon 1 and carbon 3 is where we have our double bond starting. So this is a 1,3 cyclopentadiene. Notice we stick that E back in. It would be called cyclopentene, but when we have the diene or the triene, we put the A back in just because it's easier to read that way. So it's called cyclopentadiene or hexadiene or some such thing. Okay, now another thing that we need to be concerned with double bonds is the fact that we can have stereochemistry associated with a double bond where if we have 2 groups, remember we have like cis or trans as a relationship that those double bonds can have. Now all the examples here don't have that shown. This molecule can have cis-trans isomerism, but I haven't shown one particular stereoisomer, right? I haven't shown the geometry of this molecule. I've drawn this as a linear molecule with these bonds hanging straight down. So we wouldn't be able to tell whether which stereoisomer I was dealing with here. Okay? Now, and when you have a double bond in a ring, in a 5 or a 6-membered ring, that double bond has to be cis. Those 2 alkyl groups have to be pointing in the same direction in order for them to reach each other and form a small ring. So this must be cis. If you are looking at a 7 or fewer for small rings, let's just say, for small rings. So we don't say that it's cis cyclohexane because there's no such thing as trans cyclohexane. It would be impossible to build that. Okay, but let's take a look at some examples that do have stereochemistry involved because we're going to want to include that as part of the name. Okay, now if you have an alkene simply with 2 groups and 2 hydrogens, then we could describe those 2 groups as being cis or trans. So cis means they're on the same